Okay, can you? Yeah, okay, awesome. Yeah, so this talk is about fuzzing substrate runtimes. This talk is about fuzzer that we have open sourced that you can today all use. The idea is to show you how it works, show you how fuzzing works, and show you what we have found so far with the fuzzer. So a little bit about us. Myself, I'm a security researcher. I focus mostly on fuzzing and code assurance at SR Labs.
And I am Jacob. I'm also a security researcher at SR Labs. I started something like 10 years ago. And in the past, I have worked on quite a number of different other projects. Some of you may remember me from Bad USB in 2013. And I've worked a lot on embedded device security, but now since a couple of years, I'm doing mostly blockchain security, mostly for Parity.
About the company, we're a rather small company. We're 50 people, mostly in Berlin. Some of us also in Hong Kong. And yeah, we've been doing blockchain since a few years. So the agenda of this talk is, firstly, we'll introduce coverage-guided fuzzing, which is the kind of fuzzing that we do for substrate runtimes. Then the typical issues that we have found in the past and that we still find right now in the runtimes of multiple parachains. Then we'll introduce the substrate runtime fuzzer, the open source implementation, a small demo of it, and also of Ziggy, which is the fuzzing tooling that we also open sourced and are using for the substrate runtime fuzzer. And then we'll also weigh the strengths and weaknesses of the fuzzer and what can be found and what cannot be found, and some takeaways from this talk. So about fuzzing. Fuzzing is a technique to test out usually a binary or some source code that you have. In our case, everything is open source, so you can do coverage-guided fuzzing because you have the source code that you can use for coverage. The idea is to seed the engine, which itself will mutate the seed, and this mutated seed will then be run against the binary. In this case, it would be a substrate runtime. So the idea is that the input to the runtimes is usually scaling coded data. So what you will see is that the seeds basically are scaling coded data, and the fuzzer has to find this himself. And with the behavior, you have a loop back, and you see what are the interesting cases. And you will see that if you have more coverage with a seed that you give, then the fuzzer thinks that this is an interesting seed. Everything else that does not give more coverage is discarded as non-interesting. And this guides the fuzzer such that it's not just throwing random stuff at the runtime, right? The target program in our case takes scaling coded data and then does transactions. So the fuzzer, in the end, once it has understood how it works, will be able to call a transaction by himself. As an example of coverage-guided fuzzing, here we have harness, where we see that we have a slice of 4 bytes, and in this slice, it checks for each character, and if it's an F, then the if passes. And in this case, at first, the fuzzer will just throw some thought-out randomness at it until it finds an F. And when it finds an F, it's like, okay, my coverage is +1. So this is definitely an interesting input. So the fuzzer will continue by directly taking F and putting more data at it. At some point, it will be the same with FU, continue with FU, until you have FU ZZ, and here we can imagine that a crash condition occurs, and then we have a crash, and the fuzzer will say that this is an interesting thing that we have to take a look at. What you need to understand is that what we are searching for is either a crash, or we can create ourselves crash with invariants. So you can say, okay, in my parachain, if this thing is like that, and then you have 20% of that, then this is a case that is impossible, and we would like to crash on that. So if we are able to do a series of transactions that occur and then this situation occurs, then we would like to have a crash. So in this case, we would do an invariant, and it would crash on this invariant. Now, the typical issues that we find with the fuzzer.
Yeah, so let's take a look at some typical bug categories of things which can go wrong in a blockchain environment. And some of these things can be found by fuzzing, some other things cannot be found by fuzzing, at least so far. So let's start with user-reachable panics. If you have some extrinsics in your blockchain with your custom business logic and you can call it with some specially crafted parameters to cause a panic, then this can be used for denial of service against block production, and it can basically take down your blockchain. So this is a critical denial of service vulnerability. Another thing which can also be found by fuzzing is unsafe arithmetic. So if you do, let's say, a standard addition in Rust, then you will have an overflowing addition, and it will just overflow without a warning, at least in a release build. And this can have a quite important business impact if it happens with, let's say, a balance. So you have to make sure this doesn't happen, and you can do it either by using saturating arithmetics, if in some cases, or by using checked arithmetics. We will see more about that later. And another thing is about logic bugs leading to a panic. So these things can be found by fuzzing, and this is the main focus of this talk. But there are also some things which cannot be found by fuzzing, at least not so far. One of these things is resource exhaustion. So if you get your weights wrong for an extrinsic, this could also cause denial of service by a blockchain if a call uses a lot more resources than the blockchain expects it to use. Another thing is having bugs in custom business logic, and this can, in some cases, lead to direct financial losses, and an attacker can directly steal money from your users, but this can typically not be found by fuzzing. And another thing is storage bloating. So whenever you allocate some storage in your blockchain, you have to think about the cost of the storage, because you need to keep it in your storage for the next 20 years or longer. So you should have a storage deposit for it so that the user has to pay for the storage usage on your chain. And this is sometimes missing. We are quite often finding it during our security audits, and this is also something which cannot be found by fuzzing so far. So let's take a look at some example things. So here we have an integer overflow. So this was an old vulnerability fixed long ago. But this was in the bridges implementation, and you would submit a relayer would submit a vector of messages, and this code would go through these messages and take the weight of each message and sum it up. And this sum can actually have an integer overflow, so you have more than the maximum value for the weight. And if this overflows, then the chain thinks, okay, this weight is well in the permissible range, so it can try to execute these extrinsics, even if they are vastly overweight, and this can hold the chain. So this could easily be exploited by sending messages with very high weight, and so that it would overflow. But this is fixed long ago. So let's see what people are doing to avoid that kind of integer overflow. Here we also have an example from the bridges implementation, and you would also submit a number of messages, and you do a checked sub here. So a checked sub will basically do a subtraction, but if it overflows, it returns a none. And if it is successful, it returns a sum with value. And then, so here you have the number of the last message, the number of the first message. And then it adds a 1, because the ranges are inclusive. So the number of messages is the difference plus 1. And if it overflows, it says, okay, it continues with the number 0. And this can actually be a problem, because you could have a situation where end is the U64 maximum value, begin is 0, then this checked sub will not overflow. It will result in the U64 max, and this addition with 1 will overflow. And with overflow means that the checked add will return a none, and the unwrap will continue with a 0. And if you actually submit 0 messages, then it will think everything is okay. It will pass this check, and then it will allocate back with U64 max as a capacity, which will obviously fail at the memory allocation. It's just too much. So you will basically crash the chain with that. So even if you have checked arithmetics, you have to be very careful about what to do if you have an overflow. And in many cases, it's the safest way is just to return an error from your extrinsic so that the whole call will fail and get rolled back by the substrate runtime. So let's see it, and let's take a look at another example in another chain we have worked with. Here you could place a bit as an extrinsic, and the fuzzer is actually found this. So this function will convert from a given amount in dot to another token with a multiplication, and it will unwrap. If you're a Rust developer, you will probably know if you have an unwrap, it will directly panic if it is a non-value. And having a user-reachable panic in a blockchain is really, really bad. So you could just submit a bit with a very, very high value, and this multiplication will overflow, it will panic. And if you submit that as a normal extrinsic to a mempool, it will normally panic when trying to build a block, and this will make honest collators fail to produce a block. But at least you can still recover by having an emergency patch in the collator runtime to just exclude that bit and still produce blocks. But if you have a parachain, you're also processing incoming XCM messages from other parachains. And XCM messages can call pretty much arbitrary substrate extrinsics. So you could actually submit a bit as an XCM message from another parachain to your target parachain. And then if your runtime is receiving an XCM message, and then the runtime code will make sure that this will actually be executed. So there's absolutely no way to make a valid block which is not executing an incoming XCM message. And so if an attacker exploits it that way via XCM, then your chain will be permanently stalled and needs a hard fork to recover, or basically relay chain governance could rescue your chain, but without that, the chain will be stalled. So let's continue with Bruno.
So about the substrate fuzzing, the fuzzer for the substrate runtimes. So how it works. As Jakob explained, it is able to actually find calls and put calls together. So how did we make that this is actually possible? So the idea is that you want to have scale encoded data that is given to the runtime. But if you have only one extrinsic that can be called, then the complex cases cannot come. You can imagine something like first you bid, and then you lock something, and then you bid again, and then there is some kind of thing that happens a few blocks later. So you want to be able to have a fuzzer that submits multiple extrinsic, but also on multiple blocks, and be able to skip also multiple blocks. That we say, okay, something will only be unlocked in like 15 blocks, so we need to be able to skip those two. So what we thought is that we'll just separate the extrinsic with ASCII stars, and if we encounter these ASCII stars, we just iterate to one extrinsic more. So a typical seed will look like that we have an extrinsic, then some stars, then another extrinsic, and then some stars. Then we will just iterate over that and execute those extrinsic, and then also finalize a block. Then when we have split it through these delimiters, we also want to have the possibility of skipping the block. So in our seed format, before both the scale encoded data and possibly the stars, you would want to have something that we call a lapse. So it's just, I think, U16, where we just say, this is the number of blocks that I want to skip. So the fuzzer has the possibility to just choose, now I skip this number of blocks. If this lapse is bigger than 0, then we finalize the blocks until now, and we skip the number of blocks that the fuzzer has told us to skip. With that, we are able to have a very good coverage, and evidently the extrinsic will be mutated by the fuzzer. Now comes Ziggy. So Ziggy is this tooling that we have also open source that I will present later, which gives us the possibility of using both AFL++, which is a very well-known fuzzing engine, which contains multiple mutators, as well as HongFuzz, which is the fuzzer from Google, I think, which has different mutators. And Ziggy gives us the possibility of creating with the same harness both HongFuzz target and AFL++ target. In the future, we will also maybe add some other fuzzers like libAFL, maybe libfuzzer. We had libfuzzer in the past, but we had some problems with it, so right now it's not there. So yeah, all of this then is given to the target. The target sees if it's something interesting, and if it finds a crash, then we save this crash, run it into GDB, or debug it however you want, and see why it did crash. And if it crashed because it was a vulnerability, then we also would share that vulnerability. So this is now open source. The entire fuzzer, as well as the harnesses. So we have 4 harnesses. We have the kitchen sink fuzzer. So why did we do that? Kitchen sink activates almost every pallet. So to have good coverage and good seeds, it's very interesting to have this. You can also see, what kind of stuff the fuzzer is able to find. Kusama, because why not? Kusama is also more bleeding edge than Polkadot, so why not? The most interesting one, I think, for the people in this room is the node template fuzzer. So the node template is what you would use to create your own parachain. And you can just directly use this harness and put it for your own parachain if this is what you want. This is usually what we do for the SBP. The only thing that you need to do is to configure the Genesis config that you have. For example, if you have certain accounts, basically what we do with the fuzzer, you will see, is that we give unlimited money to the fuzzer such that he can actually do something, right? So this is the stuff that you will need to do if you have some NFT things going on, then you would like to create some NFTs such that he can sell them or bid them somewhere. Then we also have a state mine fuzzer, which I think is also interesting. So this is something you can directly use. So for the second tooling that we have open source, this is open source since some time now. This is not blockchain specific, it's just a helper to fuzz. It is quite easy to use. You have multiple tooling. It generates coverage for you. You can add more seeds while the fuzzer is running. It creates both HongFuzz and AFL++ for you. And you just have to do cargo Ziggy fuzz, and it fuzzes your thing. The harness looks like a macro. Yes, it is a macro, sorry. It's a macro, which is called fuzz. And inside this macro, you put all the harness code, and then the input to this macro, which is a parameter, it's a slice of U8. You can just take that and parse it into a scale encoded data and use it as an extrinsic. Okay, so now I will do a little demo, if the demo gods are with us. Okay, so what we can see here is the fuzzer that I have started a few hours ago. You can see that we already have a crash that occurred, which is good for me because would have been bad if it wasn't. You can see it's quite fast. It has like about 4,000 execution per second. You can see that. So this is the AFL. For those who know AFL++, this is the AFL logs. So you can see here that AFL found one crash. That currently our map density is quite low, so our coverage is not very high. Keep in mind that the part of the runtime that is actually the interesting code is rather small compared to Substrate, right? So you would want to have your pallets in there and not specifically the Substrate code. And yeah, we have one crash. And here you can see this is the same thing, but for HongFuzz. In HongFuzz, we have not found any crashes, so the crash that we have found was found by AFL++. And this is the new coverage that we have, if I can find my mouse. This is a line that is printed every time a new coverage has been found by HongFuzz. So I have already made an example. I will show you the code. Maybe we can do this right now. So you can see that if I run this crash, so this is the runner, and I just run the crash itself. If I run this, you can see that we print what calls did the fuzzer do. So you can see it's initializing the first block, setting a timestamp because we need to set a timestamp. This is the origin of our fuzzer. So our fuzzer has unlimited money on this account. And you can see it's doing a runtime call do something, something with a conspicuously high number, and then a call cause error, which causes the error. So if we take a look at that file, you can see that it's a palette that we have. So it's the node template palette. And you can see that the do something call just puts something in storage and then returns a successful dispatch result with post info. And in the code cause error, you can see that we commented out the safe way of doing it. So with a checked add, and if it doesn't work and it overflows, we throw an error with a storage overflow. And here we replaced it with a new is equal to old plus 1, which is unsafe. And you can see that of course, without, so the fuzzer started raw, we didn't even give him anything, and he was able to find that if he puts something to U32 max, -1, I think, then the +1 will overflow in the cause error. So you can see that trivially our fuzzer found this error, which overflowed in this case. So let's take a look at the harness itself. So if we start from scratch, you can see it's a lot of code. Don't be afraid. This code is mostly boilerplate code. What we do is we try to initialize with things that are smart. Like we don't want that the fuzzer does unlimited blocks, right? We don't want to. We know that we will not have more coverage if we just skip a zillion blocks, right? So what would be interesting is to have compact blocks that maximize the coverage that we can have. So what's happening here is that we know that there is also a max time for blocks, so we would also crash if we exceed that time. And you can see that here we have the stars delimiter that we take. So here you can see that we just create an iterator that iterates over the data and checks that you know, some limits are not gone over, because the fuzzer would, you know, just try to do bigger and bigger inputs, which is not something that we would be interested in. And you can see that here we implement a simple iterator that takes the data and splits it over the star splitter, as I explained. Here we have our main function. So the code I'm presenting right now, just so keep in mind, this is the open source code. So this is the node template fuzzer. So here we create 5 accounts. We want to have 5 different accounts that the fuzzer is able to use, because of course you want to have the possibility to do a transaction from A to B. And then we have the Genesis storage. So this is something that, as a parachain, it would be very important for you, because this is the place where you have to add your code. The code here, you can see that in the Genesis config, what we do is we have palette balances, we have palette aura, we have palette grandpa, which is all stuff that we have implemented ourselves. But of course, the palettes that you have in your parachain is something that you would like to implement here if your Genesis config has a specificity. So you can see here in the palette balances, we just put our account, and you can see a little more down. You can see that this is the actual macro that I was telling you about, Ziggy Fuzz. This is an input. This is the closure of the input for the fuzz macro. So it's a function. So it's a closure, which is the function that we give to the macro, which is actually the harness itself. And you can see that the input to this function is called data and is just bytes. So what the fuzzer sees, what AFL++ sees, is just bytes that he can give. There is a limit to that. I think the inherent limit to AFL++ is 1 megabyte. So you can imagine that, yeah, 1 megabyte should cover all the cases that we are interested in. You can see that we do some boilerplate code on, we want that the weighting of the block is not too much. If it's too much, we don't include it in the block, because obviously that would not be something that is a finding. And then you can just see that we iterate over with our iterator over all the extrinsic that we have. And then for each extrinsic, we split it. So as I said, the first 4 bytes are the lapse, how much blocks we skip. The origin, so this is a U16. We only want the origin to be the accounts that we have configured, because obviously he can always do more accounts, but those accounts will not have funds and nothing will happen. So we just do a modulo, and in this modulo we say, okay, if this modulo is a bit further down, but you will see that we just say, okay, it has to be one of these accounts, and if it's not, it's just modulo the size of the accounts that we have, so that we always have an origin that is something from us. And then basically we just take the rest of the data and decode it in scale for each extrinsic that we have in the iterator. When we go a bit more down, you can see that once we have the encoded extrinsic, we decode it with a max limit of 64. There is no point in making nested calls at some point more than 64. We will not find any more things. We've seen that 64 is basically where we stop finding stuff. And yeah, basically then it's only boilerplate, right? You try to create a block and then include a timestamp, include your extrinsic, and if you can see, if we have a lapse, then we skip the number of blocks. We set the timestamp to timestamp plus the lapse that we just jumped, and basically we just execute the extrinsic, sorry, which is here. And yeah, basically that's it. And if this crashes, then we want to have something that prints out. So there's 2 ways of compiling it. The first way is the fuzzing. So we don't want to have any syscalls, so we don't want to have any prints or stuff like this. But when we debug it, we would like to have a lot of debug info. So when we have a crash, you saw it prints out a lot of stuff, which is just the print here, which will be compiled inside with a feature set, and this feature set is only set if we compile the runner. Yeah, and this is basically it for the demo. Yeah, and as you can see, it is able to find quite quickly crashes, even if they are U32 max. Okay, so now on the strengths and weaknesses of the fuzzer.
Yeah. So let's take a look at what the fuzzer can do and what the fuzzer cannot do for you. So
oh yeah, sorry, this is mine. So we also talking about what we can find and we cannot find. An interesting thing is to see the statistic, right? What have we found? What have we found about with the fuzzer, and what have we found not with the fuzzer? And you can see also the categories of stuff that we find. So if you are a parachain developer, you would want to take a look at your benchmark, because we find a lot of benchmarking issues. So benchmarking issues is not something we find with the fuzzer, but it is the thing that we find the most. So that's something that is very interesting. But as you can see, the next categories of stuff that we find is arithmetic issues, findable by the fuzzer, reachable panics, findable by the fuzzers, memory issues, mostly not findable by the fuzzers. We are working on it, but you will see Jakob will explain a bit on the categories, and then some other possibilities, namely also storage issues is a big name here. So yeah, the fuzzer is a big part also of findings, specifically for stuff that is very tedious to find, for example, all the arithmetic issues that could occur, also the very nested cases that could occur, and the fuzzer is very, very good at that.
Yeah, so let's take a quick look at the different methods we use during our assessment. So we have basically 3 options to analyze a blockchain project. One is static analysis, one is fuzzing, and one is manual code review. So for static code analysis, we can find some issues, but it's also hard because it has a lot of false positives. So for example, we can find wrongly priced transactions in cases where you have just the default weight of something like 10,000 or even 0 at a weight annotation. This is something which can be found via static code analysis, but other errors cannot be found. Also for unsafe arithmetics, in theory it could be found via static code analysis, but in practice it will result in quite a lot of false positives, and many things are still pretty safe and cannot be reached. So you may end up with hundreds of potential issues and need a human to actually analyze all of them and find out if anything is a real issue or not. The same also applies for reachable panics. This can be found via static analysis, but sometimes it also gets too many false positives. And also logic errors, it also depends on, and storage bloating cannot be found via static code analysis so far. For fuzzing, we can definitely find unsafe arithmetics. That's what we are finding quite a lot. And we can find user reachable panics. And we are also working on finding other things like a mismatch between the transaction weight and the actual weight. So, for example, the POV size or maybe even the execution time. And also for storage bloating, we may want to extend the fuzzer to detect how much storage a substrate call is using and see if we can find these kind of bugs. But this is still work in progress, but we may extend our fuzzer to do that. And when we have manual code review, it's taking a lot more time than static analysis and fuzzing, but it can find basically everything, and especially for logic errors in custom business logic, it's often the only way to find these bugs. So it is still important, and so as a takeaway, the static code analysis and the fuzzing is something which should be tightly integrated in the development process and start early on. But before doing an actual economic launch with real money behind it, there should also be a full audit, including manual code review, especially with custom palettes, custom business logic, and so on. So let's take a look at an example of a bug which could only be found via manual code review. So this is in the Substrate smart contracts palette, and as all the bugs presented here, it has been fixed a long time ago. So for this bug, you would, when calling a contract, the smart contracts palette would check if you have enough balance to pay a storage deposit. Because whenever a smart contract adds some storage, there needs to be a storage deposit, and the storage deposit needs to be called by whoever is initiating the smart contract call. And this could be something like having an ERC20 balance and a user creating a new account for this token will have to pay for the storage deposit. So in the past version of this palette, it would check if you have enough funds to pay the storage deposit. Then it would do the contract call and actually write it to storage. And then in the end, after the whole contract call stack is done, it could collect the storage deposit with the assumption that it will work because you have checked before that you have enough funds for it. So this should be safe, right? Well, not actually, because a smart contract can also call back to the substrate runtime. And an attacker could give a smart contract the privilege to actually control the calling account via proxy access, via standard substrate proxy wallet. So an attacker could make his own attacker contract and give it proxy access to a hacker account. And then this attacker smart contract could actually call a victim smart contract to insert some storage, maybe create a new token balance for a user or something like that. And then it takes the proxy access to transfer wave funds. So the smart contract pair has checked in the beginning that you have enough storage deposit, enough to pay the storage deposit, and then during the contract call, this amount is transferred away. And then later on, the contract pair wants to collect the storage deposit, and the money is not there anymore, so it fails. And in the past version, the contracts palette would just ignore this error and still keep the storage added by the contract call and not roll it back. And so a user could actually do this a lot of times. And for many smart contracts patterns, if you add an account to a smart contract, add an account balance or something like that, you're also allowed to delete the storage again. And if you delete storage from an Inc. smart contract, then the associated storage deposit is refunded. So if an attacker does this 1,000 times, and then claims a refund for a storage deposit by deleting the accounts later on, then this will actually drain the funds from the smart contracts. It's not affecting the economic funds of something like a DeFi project, but it is affecting the storage deposit paid by other users. So everyone reclaiming a storage deposit from that smart contract will get less than the adequate amount if this happens. And luckily this bug has been fixed by just rolling back the contract call. So if you roll back all the changes, then the only impact of executing it is paying for the execution weight, so you still pay the transaction fee, but you don't add anything to storage, and so it's no problem if you can't collect the storage deposit anymore.
Okay, so some takeaways. I think the biggest takeaway is that fuzzing is very useful, but it's not everything. It uncovers a lot of things that we could not uncover by hand. Specifically the panics in the runtime and the unsafe arithmetic. And this automating allows us to scale and really take a look at huge code bases and multiple parachains. So I think also the blockchain world is very in its infancy. I think in the security part. And I think it's really important to also know the security best practices of the specific chains. And I think in Substrate now we know them. We know storage deposits. We know like panics in the runtimes, and it is in Rust. So there's also a lot of others that are not affecting Substrate. But it's good to know them and also apply them when you do your own parachain. I think collaboration is also key. I think there's a lot of stuff that we don't know about the parachains, and we are also ourselves learning. And I think it's really important for us to share also what we've done and how we approach it. So we usually approach it with like a threat modeling approach. We try to attack it and say, okay, what is the stuff that we can do, and how can we do that, and then actually try that. And I think that fuzzing is one tool to try that. And we encourage you to take this code for yourself and try it out. Use that for your own parachain and find bugs by yourself.
Thank you guys for a really interesting presentation. Although I'm not a Substrate developer, I also learned a lot. And also I think that was the best prepared slides I've seen so far, so you definitely rock. So we still got some time, so do you guys have some questions for Jacob and Bruno?
Thanks for the great presentation. I didn't quite caught how you decode the extrinsic in the demo from like random bytes. How do you go from random bytes to something that can be decoded as an extrinsic?
It's actually quite simple. We use parity scale codec. I mean, there is a package for that, right? So we just take the bytes and use decode. But
it's going to fail most of the time, right?
Yeah, it will fail sometimes, but the fuzzer is great at finding cases where it doesn't fail. So the fuzzer will try different things, and then it succeeds in decoding one more byte. So it continues with that and adds some more bytes on top of that. And at some point in time, it will find really good coverage and really things which can actually be decoded.
Okay. What you explained at the beginning with the first example.
Yeah.
Okay.
I mean, it's really good at coverage. So once we have the coverage of parity scale codec, then we're through, right?
Okay. So the longer the extrinsics, the longer it's going to take for the fuzzer to find some things that can be decoded?
No, I mean, fuzzers are really smart.
Okay.
Like it's really very smart ways of mutating. It's not just flipping random bytes, right? It knows there is a thing called, for example, comp log. So you have a thing where it sees in the code, okay, we have a comparison of 32 bytes, so I should probably add 32 bytes here, right? And these kind of smartness are, I mean, it's not the only smartness, right? Actually, complog is something we're trying to activate because we only have like a mini kind of complog activation, but it's really good at knowing, okay, now we need probably like 32 bytes or like something that is ASCII, or it's really good at that, yeah.
Thanks a lot.
Hey, hi. I had a question about the vulnerability regarding like wrongly priced transactions. So basically the weights don't match what the benchmark says. You said that you're planning to try using fuzzing to detect these vulnerabilities. Like at what level? Can you add some more information, and like what's the main challenge here?
But it is still in the early stage of it, and what is relatively easy is to go for a POV size. We would just have to record the POV, what kind of access it needs, how many storage items it needs, and how big these storage items are, and then compare that with the POV size weighting. And we are also thinking about whether it is possible to do something for actual execution time, but it is not yet finished.
And in this case, you can see that the overflow code is just in the weight calculation. So the fuzzer will, go there and see an overflow, because this code is just like any other code, right, for the fuzzer, and find a crash. And then we will analyze it, and we're like, okay, this is weird. And in this case, the thing that has overflowed is weight related, and there is a way of making the weight very small, which is not okay in this case. Yeah.
I'm curious, do you have any thoughts on integrating this especially with the amount of time that it takes to run, integrating it with a continuous delivery system? So you might run this fuzzer every time before you cut a release or something like that.
I mean, it's definitely a possibility. I think we've talked a bit about these things with Vince. I think that it's definitely a possibility. It takes a lot of computing power. So, it depends what you want to do. And sometimes it takes a lot of grooming, right? We're saying like, oh, it's easy, you can just throw. Fuzzing takes a lot of grooming usually. So it's definitely something we would like to do, but it's not just something you can do easily. So, we constantly every week we're like, we don't have very good coverage in this. Like for example, precompiles when we fuzz is something that the fuzzer is like finding, but not really good compared to other things. So we kind of try to help it a little by crafting ourselves like the bytes that it needs, and then we have a little Python script to do that. And so yes, definitely we're taking a look at that. Yeah.
All right. Do we have?
Thank you. I didn't understand the demo very well. So the chain had the no template was for the chain, and the runtime was for the chain, and then the code that you showed us that was initializing your grandpa and then making the block and doing, where does that sit? Is another palette which is not, because it should be controlling the block. Where is that?
It is in a palette.
So it's a palette, okay.
I can show you again the code. It's if you see the call itself, it is the call do something. We have patched a call called cause error. So we've created an extrinsic called cause error, where we just make something that overflows, and this will then overflow. So you can see that it also answers your question, right? The fuzzer was really good at this. It was able to create first the call do something, and then the call cause error. Because if you saw the code before, the only way of doing this error is to have both extrinsic called and in the good order and with the good parameters, because this is the parameter that overflows in this extrinsic. So we need to do both things. So it does sit in the palette, okay. And the code that was given is scale encoded data this, then stars, then scale encoded data this, and then it crashes.
So from the palette you can call the benchmarking? You can't, can you? No.
I mean, you could do that. The thing is that, like, what do you consider a crash?
Yeah, I understand.
Right? Like, usually it literally crashes, it panics in the cases of Rust. Or you put an invariant and you say, okay, please crash if the total number of money has increased or something. Yeah.
But it is a call from runtime into runtime, which does the benchmark.
I didn't hear.
It's a call from runtime into runtime that does the benchmarking, basically. It runs the benchmarking code.
I mean, this is not benchmarking code. It's just it's just an extrinsic call.
So the extrinsics are with runtime, but the benchmarking you run it differently.
Yeah, that's different. Yes.
Thank you.
Thank you for the presentation. One question: is it possible to import the current state of the chain and run the fuzzer based on the current state that we already have?
I think it's not possible at the moment, but it is one thing we have thought about it for a long time, and we may implement that in future.
Yeah, I think it's difficult. Like the thing is that you would want to extract like the Genesis config of a chain. We do parse like the wasm blob with this sub-wasm thing, and you try to like. There's a lot of stuff that you can do, but the thing is also that sometimes like we need to add our things on top, like have these accounts that we pre-fund, and we also don't want to have a mock environment, so we want to have the actual environment, but we also want to compile it such that an overflow would crash, which is not the case in it's only the case if you have a debug build and not a release build in Rust, and we do it in release build because fuzzers need to be efficient. So we just add a flag such that it does still crash in these cases. So importing that is not just we can take it and import it. I think, yeah, like you said, we've thought about it and it's difficult, yeah.
Yeah, and it also needs a lot of data because on a real life blockchain you may have 100,000 accounts, and then the fuzzer would have to try it again with 100,000 accounts and even have a way to find these accounts. So you could engineer something that the fuzzer just gives a U32 index and it will just use that modulo, the number of accounts and so on. You could do that, but it will also make fuzzing a lot slower because the fuzzer needs to try a lot of accounts.
All right, so maybe we have a space for one more question. Anyone?
Thanks for the presentation. It's not fuzzing related, but symbolic execution related. Have you tried those techniques? Do you have some experience with that? Because that would be super interesting for me if you tell me about that.
So there is the possibility of doing that with AFL, for example, because AFL has these kinds of targets. It's not dependent on our fuzzer. Like what you do is, in the end, the fuzzer is just you compile your code in a very specific way, such that AFL and HongFuzz appreciate that, and then you just take AFL fuzz and you pipe the binary to it, and then AFL fuzz does its magic, and HongFuzz does its magic. So AFL has the possibility of doing this kind of stuff. So nothing, you could just use AFL and do that. You just need to configure it yourself. So we use AFL.rs, which is maintained by a guy from Trail of Bits, I think, and it's not included there. So you would have to make a patch request probably for that, but I don't see why not, yeah.
So for Substrate, you don't have any symbolic executor tool right now?
Not currently, no.
Ah, okay, thank you.
Yeah. All right, maybe I'll try to very last one. Like in the beginning, you mentioned like you observed like a different behavior if the call was made via XCM in opposition to if it was made like locally. So does it make any sense to actually use the fuzzer via XCM and do the remote calls from the other chain, or it actually doesn't make any sense and the result would be the same?
Well, it is certainly possible to do fuzzing via XCM and actually fuzz the incoming XCM instead of fuzzing incoming extrinsics. But for its difference in behavior, it was just that if you have a panic locally, then your chain is not stalled because you could still produce a block just not including the problematic extrinsic. But if you have incoming XCM, you are forced to execute it. You just can't make a valid block without executing this incoming extrinsic. And so your chain is permanently stalled if it would automatically panic while executing it.
Yeah. All right, thank you. Yep. So I suppose that's it. We are right on time. So thank you very much, guys, for a wonderful presentation. And yeah.